Module 10, Lecture A, Algorithm Design. By the end of this lecture, you will be able to decompose complex problems into subproblems that suggest suitable algorithmic techniques, select appropriate data structures and algorithm paradigms for given Python problems, and communicate algorithm designs clearly using high-level descriptions and complexity analysis. Decomposing complex problems, clarifying problem requirements. When turning a complex task into an algorithm, the first step is to clarify the problem requirements. You must understand exactly what is being asked and what is not, turning vague goals into precise specifications. For example, in a recommendation system, you need to decide whether the main objective is to increase sales, user engagement, or diversity. And in scheduling, whether you care more about finishing tasks quickly or balancing workloads. Each choice leads to different algorithmic solutions. So without this clarity, you may end up solving the wrong problem. When clarifying requirements for an algorithm, you need to define inputs, outputs, and constraints clearly. Identify what information is available, how it is represented, and what assumptions you can make about its size and reliability. For instance, in a navigation app, you must decide whether the road network is static or changes over time, and whether real-time updates are required. You should also specify what the algorithm must produce, such as a single best answer or several options. Finally, constraints like time limits and privacy rules guide the algorithmic design and help turn vague challenges into well-structured problems. Clarifying requirements means uncovering hidden structures and priorities, especially when stakeholders have conflicting needs, such as wanting a system that is both fast and accurate, or personalized yet anonymous. Your role is to ask targeted questions and negotiate trade-offs so these needs can be expressed in precise, algorithm-friendly terms. In a university course allocation system, for example, you must balance student flexibility, instructor preferences, and administrative rules. By separating strict constraints from optimization goals, you can break the task into subproblems, like checking feasibility and assigning priorities, which then guide the choice of an appropriate algorithmic approach. Core operations breakdown. Once you understand what a problem is asking, the next step is to identify the basic operations needed to solve it. These are simple, repeatable actions such as comparing items, updating totals, or moving through a structure. Many tasks boil down to scanning collections, filtering out certain elements, or keeping track of the best option found so far. Recognizing these recurring patterns reveals the computational structure of the task and helps you connect real-world problems to general algorithmic strategies. When designing an algorithm, imagine explaining the task as a sequence of simple actions that turn inputs into outputs. For example, a movie recommendation system might look up user ratings, compare them with others, compute similarity scores, and then rank movies, while a logistics system might choose the next stop, estimate travel times, update which locations are served, and revise plans. By stating these actions explicitly, you can spot patterns such as selection, ranking, and updating. These patterns then point you towards suitable algorithmic techniques, like greedy selection or dynamic programming. By breaking problems down into their core operations, you can see which tasks are most demanding and which matter less, helping you focus your design and choose suitable algorithms. In areas like text analysis, this might mean emphasizing word counting and frequency comparison, while in financial modeling, it might mean focusing on transforming data and summarizing results. Noticing recurring patterns, such as frequent lookups or updates, lets you match your problem to known algorithms and data structures. With practice, this systematic approach connects informal problem descriptions to efficient algorithmic solutions. Python code, core operations breakdown. This lesson focuses on how to break complex tasks into simple core operations using Python lists. You will see how real-world style problems can be solved by repeatedly scanning through a list, selecting certain elements, aggregating values such as totals or counts, and tracking the best or most extreme values. By connecting these everyday problem-solving steps to their underlying algorithmic building blocks, you will better understand how list processing supports more advanced programs. This line in the script is just a placeholder where a pip install command would normally go. It does not actually install anything or perform any real action. Its main purpose is to keep the script's format consistent and to show where package installation commands could be added in a real project. In practice, you would replace this placeholder with an actual command if you needed to install a package. We begin with a list of dictionaries where each dictionary represents one movie and stores its title, rating, and genre. The rating is given as a floating point number, and the genre is stored as a text label. This structure simulates movie ratings from different users and keeps all related information for each movie together. Using this format makes it easy to access, filter, and analyze the movies based on criteria such as genre or rating. To keep only science fiction movies from a larger movie list, we first create an empty list that will store the filtered results. We then go through each movie in the original list and check its genre. If a movie's genre is science fiction, we add it to the new list. By the end of this process, the new list contains only the science fiction movies we are interested in, and all other genres have been filtered out. To find the average rating of the filtered science fiction movies, we first set up a total rating value starting at 0. We then go through each movie in the filtered list and add its rating to this total. Once all ratings have been added, we divide the total rating by the number of movies in the filtered list. This final result is the mean rating for the science fiction movies. To find the highest-rated science fiction movie, we start by assuming we have no best movie yet and use a very low placeholder rating. We then go through each movie in the filtered science fiction list and compare its rating to the best rating we have so far. Whenever we find a movie with a higher rating, we update both the best rating and the best movie to this new one. By the time we finish checking all the movies, the stored best movie is the one with the highest rating among the science fiction options. We first report how many science fiction movies met our filter criteria, giving a clear count of the matching films. Then, we calculate and announce the average rating of these filtered movies, rounding it to 2 decimal places so the result is easy to interpret. Finally, we identify and state the title of the highest-rated science fiction movie in this group, summarizing which film performed best in our analysis. This script works with a list of movies to show how basic data operations can answer useful questions. It first filters the list to keep only science fiction titles. From these, it computes the average rating by adding their ratings and dividing by how many there are. It then finds the single highest-rated science fiction movie by comparing their ratings. When run, the script reports how many science fiction movies were found, their average rating rounded to 2 decimal places, and the title of the top-rated one, illustrating how simple steps can solve more complex tasks. Recognizing algorithmic patterns. Recognizing algorithmic patterns means looking beyond the story of a problem to see its underlying computational structure. Many tasks in areas like logistics, finance, and social media reduce to common patterns such as searching, sorting, or optimizing, often involving graph traversal or optimization. By reframing a problem as questions like whether you are finding the best option or exploring connections, you can match real-world situations to known algorithm families. This makes complex problems easier to handle because you can apply established techniques instead of inventing solutions from scratch. To build pattern recognition in algorithms, focus on the core operations of your problem and connect them to familiar solution types. If you often access items by a key, think in terms of dictionary or hashing patterns. And if you track a current best option, consider priority queues or greedy methods. For problems based on pairwise relationships, such as matching jobs or comparing documents, look into matching or clustering approaches. Over time, create a mental catalog of patterns, like graph search for maze-like tasks or dynamic programming for sequential decisions, and map new problems onto this catalog instead of treating each one as completely new. Recognizing algorithmic patterns means identifying which standard techniques match the different subproblems in a complex system, such as searching large datasets, optimizing routes, or updating information in real time. By naming these patterns explicitly, you create a shared language for design discussions and can rely on well-understood algorithms and trade-offs instead of inventing fragile, one-off solutions. This lets you efficiently solve tasks like shortest path and scheduling problems by drawing on existing knowledge rather than starting from scratch. Choosing algorithm techniques, greedy or dynamic programming. When solving problems that involve a sequence of decisions, you must decide whether a greedy strategy is enough or if you need dynamic programming. A greedy algorithm always takes the best-looking local option, which is simple and fast, but only works when these local choices also produce the best overall result. In many problems, though, an early choice can limit or damage future possibilities, so local decisions are not reliable. Dynamic programming handles these complex interactions by exploring combinations of choices and storing intermediate results to find an overall optimal solution. This approach uses more time and memory, but provides greater accuracy and robustness across a wider range of problem types. To choose between a greedy algorithm and dynamic programming, focus on how decisions affect the overall solution. If you can make each choice based only on local information, never need to revise it, and it still leads to the best overall result, a greedy method is appropriate, as in simple coin change or appointment scheduling. However, if earlier choices influence what is possible or optimal later, or you must compare many combinations of decisions, dynamic programming is better because it systematically handles these dependencies. Dynamic programming is useful when a problem has overlapping subproblems and an optimal substructure, meaning the best overall solution can be built from smaller, repeated parts. This often appears in planning tasks, such as complex road trips, financial optimization, or supply chain decisions, where each choice affects future options. In these cases, greedy methods that only look at immediate gains can miss better long-term outcomes. Dynamic programming instead systematically explores and stores the best results for recurring states, allowing you to capture the full complexity of the problem. With experience, you can quickly test a greedy approach and switch to dynamic programming when you see that long-term effects matter. Python code, greedy or dynamic programming. This lesson compares greedy and dynamic programming approaches to the coin change problem. It shows how a greedy strategy, which always picks the largest possible coin first, can make locally good choices, but still miss the best overall solution. In contrast, dynamic programming systematically explores combinations to find the minimum number of coins, guaranteeing a better global answer. A simple, beginner-friendly example is used so learners can run and experiment with it directly in a Google Colab environment. The script explains that you do not need to run any pip install commands because it only relies on standard Python libraries. In other words, it is designed to work with the default Python installation without extra packages. This makes the code easier to use and more compatible across different systems. It is especially convenient in environments like Google Colab, where installing additional libraries may be limited or inconvenient. We begin by defining the standard U.S. coin denominations in cents: quarters, dimes, nickels, and pennies. These values form the basic set of coins we will use in the coin change problem. The goal of this problem is to make a specific amount of money using the fewest coins possible. By establishing this list of denominations, we create a clear foundation for comparing different algorithms that try to solve the coin change problem efficiently. Consider a coin system with denominations of 10, 6, and 1 cent, which is designed to be difficult for a greedy algorithm. A greedy method always picks the largest coin first, but with these values, that strategy can fail to find the fewest coins needed to make a given amount. This example shows that local, step-by-step choices are not always optimal. It also motivates using dynamic programming, which examines combinations of coins more globally to find a truly optimal solution. This function uses a greedy strategy to choose coins for a given amount. It first sorts the coins from largest to smallest so that it always tries to use the largest coin available. It then goes through each coin, figures out how many of that coin fit into the remaining amount using integer division, and if any can be used, it adds them to the solution. After each choice, it subtracts the total value of those coins from the remaining amount. This continues until the amount reaches 0 or there are no more coin types to consider, and the function finally returns the list of chosen coins as the solution. To solve the coin change problem with dynamic programming, we first choose a very large placeholder value that represents an impossible number of coins. We then create a list where each position corresponds to an amount of money and initialize every entry with this large value. This list will store the minimum number of coins needed to make each amount. Finally, we set the entry for amount 0 to 0, establishing the base case that no coins are needed to make a total of 0. To solve this problem with dynamic programming, we build up from 1 cent to the target amount. For each amount, we look at every coin denomination and check whether using that coin would stay within the current amount. If it does, we compare the current stored number of coins with the number of coins needed for the remaining amount after using this coin plus 1. We then keep the smaller of these values. By repeating this process for all amounts and coins, we ensure that each entry stores the minimum number of coins needed to make that amount, up to the target. The code uses a dynamic programming list to track the minimum coins needed for each amount. At the end, it checks the entry for the target amount to see if it is still set to the initial maximum value. If it is, this means no combination of the given coin denominations can exactly make that amount. In that case, the function returns none to indicate the amount cannot be formed. To reconstruct the optimal sequence of coins from the dynamic programming solution, we start with an empty list for the result and set the current amount to the target value. While the current amount is still positive, we scan through the coin denominations to find one that does not exceed the current amount and that corresponds to the optimal choice recorded in the dynamic programming table. When we find such a coin, we add it to the result and reduce the current amount by that coin's value, effectively stepping backward through the solution. We repeat this process until the current amount reaches 0, at which point the result list contains the optimal set of coins for the given amount. The compare system function evaluates two methods for solving the coin change problem: a greedy approach and a dynamic programming approach. Given a set of coin denominations, a target amount, and a label, it first computes a greedy solution that always picks the largest possible coin, then computes a dynamic programming solution that considers all combinations to find the optimal result. It prints which coin system is being tested, along with the coins and target amount. Then reports how many coins each method uses and which coins were chosen. This side-by-side output highlights differences in efficiency and effectiveness between the greedy and dynamic programming strategies. We compare two coin change algorithms using United States coin denominations for a target of 63 cents. A comparison function runs both a greedy method, which always picks the largest coin value first, and a dynamic programming method, which finds the solution using the fewest coins overall. It then reports how many coins each method uses and which specific coins are chosen. In this example, the results show that the greedy strategy happens to be optimal and matches the dynamic programming solution. We examine how a coin change system behaves when given a tricky set of coin denominations and a target of 12 cents. A comparison function runs both the greedy method and the dynamic programming method on this coin set and amount. then reports their results. The purpose is to show that the greedy approach can fail to find the minimum number of coins in such cases, while dynamic programming can correctly handle the complexity and produce the optimal solution. This final message reminds students why dynamic programming is powerful. It works well when choosing the best option at each step, as in a greedy method might block you from reaching the best overall answer. Dynamic programming instead looks at the whole problem space, not just local decisions. This broader view helps ensure you find the truly optimal solution. This script compares greedy and dynamic programming methods for solving the coin change problem. Using standard U.S. coin denominations, both approaches find the optimal solution with the fewest coins. However, when a specially chosen tricky set of coin values is used, the greedy method fails to find the best solution. In contrast, dynamic programming still succeeds because it systematically considers all combinations to minimize the number of coins. This shows that dynamic programming can handle complex cases better than greedy algorithms when local choices do not lead to the best overall outcome. Modeling with graphs. When you work with problems that involve entities and how they relate to each other, it is often best to model them as a graph. In this approach, entities become nodes, and their interactions become edges, which lets you treat tasks like route planning or network connections as graph problems. Once you recognize your data as a network, you can use graph-oriented structures in Python, such as adjacency lists or matrices, and rely on standard graph algorithms instead of building custom solutions from scratch. When modeling with graphs, the key design choice is what to represent as nodes and what to represent as edges, because this determines which algorithms you can apply. In a social network, users can be nodes and friendships edges, which supports finding communities or influential users. In logistics, cities can be nodes and roads edges with weights like distance or cost, enabling shortest path calculations. In course scheduling, courses can be nodes and prerequisite relationships directed edges, which helps detect cycles and find valid course orders. By mapping a problem's elements to nodes and edges, you can use standard graph techniques such as traversal and topological ordering. Once you model a problem as a graph, the algorithm you choose depends on the graph's structure and what you want to find. To explore all reachable states, such as all users influenced in a network, breadth-first or depth-first search with adjacency lists is effective. To optimize routes or minimize costs, use shortest path or flow algorithms that rely on weighted edges. To analyze overall network structure, such as clusters or key points, use algorithms that measure connectivity and centrality. In all cases, design your Python data structures, like dictionaries of lists or sets, so they efficiently support these graph operations and keep performance high. Python code, modeling with graphs. Model simple real-world problems in Python using graphs built with adjacency structures, where cities are represented as nodes and roads between them are weighted edges that store travel times. On this graph, you can run breadth-first search to explore connections layer by layer. You can also run Dijkstra's shortest path algorithm on the same graph to find the fastest route between cities based on the travel time weights. Comparing these two approaches shows how different graph algorithms solve different types of path and distance problems. The commented line mentions installing the libraries NetworkX, Matplotlib, and Seaborn, but explains that this is not needed when using Google Colab because they are already available there. It mainly serves as a reminder for people running the code outside of Colab to make sure these tools are installed for graph visualization and analysis. However, it also notes that in this particular script, these libraries are not actually used directly. We represent a small road network as a graph stored in a dictionary, where each city is a node and each road is a connection with a travel time. For example, City A connects to cities B and C with travel times of 30 and 60 minutes. City B connects to A and D, City C connects to A and D, and City D connects to B, C, and E with their respective travel times. City E connects back to D. This structure captures both which cities are connected and how long it takes to travel between them, modeling the network as a graph with weighted edges. We define a function that uses breadth-first search to find all cities reachable from a chosen starting city. To manage which cities to explore next, we use a double-ended queue from the Collections module. This queue lets us efficiently add new cities to visit and remove cities we have just explored. By processing cities in this way, we systematically traverse the graph and discover every city that can be reached from the starting point. This function explores all cities reachable from a starting city using a breadth-first search. It keeps a set of visited cities and a queue of cities to explore, beginning with the start city. While the queue is not empty, it takes the next city, skips it if it was already visited, and otherwise marks it as visited. It then looks at each neighboring city, and if a neighbor has not been visited, it adds that neighbor to the queue. After the queue is empty, the function returns the set of visited cities, which represents all cities that can be reached from the starting point. We use the heap queue module to efficiently manage a priority queue, which is crucial for implementing Dijkstra's algorithm. This structure lets us quickly retrieve the city with the shortest known travel time at each step. By keeping cities ordered by their current best distance estimates, the heap ensures we always expand the most promising city next. This makes the algorithm both correct and efficient. This function computes the shortest travel times from a starting city to all other cities in a road network. It begins by setting every city's time to infinity, except the starting city, which is set to 0. Using a priority queue, it repeatedly selects the city with the smallest known travel time and considers all roads leading out of it. For each neighboring city, it checks whether going through the current city gives a shorter total time, and if so, updates that neighbor's time and adds it back to the queue. When the process finishes, the function returns the dictionary of shortest travel times from the starting city to every other city. We choose a starting city called A as the source for our graph algorithms. Using a breadth-first search, we first find all cities that can be reached from this starting point, ignoring travel times and focusing only on which cities are connected by roads. Then we apply Dijkstra's algorithm to compute the shortest travel time from the starting city to every other city, taking the road travel times into account. We store both the set of reachable cities and the shortest travel times for later analysis or display. We display a message that shows which cities can be reached from a chosen starting city using the road connections in our graph. This message includes the name of the starting city and the list of cities that are reachable from it. We obtain this set of reachable cities from the breadth-first search function. Seeing this output helps us understand how the graph is connected from the point of view of the starting city. We go through each city in the dictionary of shortest travel times, sorting the cities alphabetically so the results always appear in a consistent order. For every city, we output a message that gives the fastest travel time from the starting city to that destination. This message names the starting city, the destination city, and the shortest travel time in minutes. Together, these messages summarize the shortest paths from the starting city to all other cities in the graph. This script represents a road network as a graph, where cities are nodes and roads are weighted edges that show travel times. It uses breadth-first search, starting from city A, to find all cities that can be reached through any sequence of roads, highlighting how the network is connected. It also applies Dijkstra's shortest path algorithm from city A to compute a minimum travel time to every other city, based on the road weights. When run, the script outputs which cities are reachable from A and the shortest travel time to each one, illustrating both connectivity and the most efficient routes in the network. Identifying search problems. In algorithm design, it is important to recognize when a task is really a search problem, even if that is not obvious at first. A search problem means exploring a space of possible options to find those that satisfy certain constraints or optimize some goal. This space might be explicit, like cells in a grid or nodes in a tree, or implicit, like all possible schedules or puzzle configurations. Phrases such as finding a path or determining whether something exists usually indicate that you are navigating a large space of states. Once you see a problem as a search problem, you can focus on how to represent states, define transitions, and specify goal states, which then guides your choice of search methods and data structures in Python. When defining a search problem, you must understand how large and structured the state space is and what kind of solution you need. Some tasks only ask whether a solution exists, while others require actually constructing one. If you need an optimal solution, such as the cheapest option, the search method must be chosen carefully. Simple search can work in small spaces, but large spaces often require heuristics or backtracking. Correctly identifying the problem type helps you pick a strategy that balances completeness, optimality, and efficiency without relying on brute force. Many real-world tasks can be viewed as search problems, where we look for states that satisfy certain constraints. Navigation apps, for example, use search algorithms such as breadth-first search or Dijkstra's algorithm to find routes, while recommendation systems search through user preferences and item attributes, often with heuristics. Puzzles like Sudoku and tasks like planning manufacturing steps also involve searching through possible configurations or schedules. By recognizing problems in this way, you can select and implement appropriate search algorithms and data structures in Python more effectively. Python code, identifying search problems. We can recognize search problems by thinking about a simple grid where we want to find a path from a start point to a goal. In this setting, the states are the positions on the grid. The moves are the allowed steps between positions, and the goal is reaching a specific target square, which together define the search space. Within this space, we can ask different questions, such as whether any path exists, how to find one valid path, or how to find the shortest possible path. This kind of example helps clarify the structure of search problems, and it can be implemented using only standard Python libraries, so no extra installation commands are needed. We represent our environment as a grid, which is a list of rows, and each row is a list of cells. In this grid, a 0 marks an open cell where movement is allowed, and a 1 marks a wall that blocks movement. Using this simple structure, we can model a pathfinding problem where we try to move from a starting cell to a target cell while avoiding the walls. We define the start of our pathfinding problem as the grid position with coordinates 0, 0 at the top left corner. The goal position is set to coordinates 2, 3 at the bottom right corner. These 2 points mark where the search begins and where it should end. With these coordinates, we can check whether a path exists between them, and if it does, find the shortest route across the grid. We represent movement in a grid using a list of direction pairs, where each pair gives the change in row and column. One pair moves the position down by 1 row, and another moves it up by 1 row. A third pair moves the position right by 1 column, and a fourth moves it left by 1 column. By applying these row and column offsets to the current position, we can navigate the grid in the 4 basic directions. The isValid function checks whether a given cell in a grid can be used. It takes a cell and the grid as inputs, then looks at the cell's row and column positions. It verifies that these positions are within the grid's boundaries and that the cell is not blocked. A blocked cell is represented by a 0 in the grid. The function returns true only if the cell is inside the grid and not a wall. Otherwise, it returns false. This function uses a depth-first search with a stack to check if there is a path from a start position to a goal in a grid. It repeatedly takes the most recent position from the stack, and if it matches the goal, it returns true. It keeps a set of visited positions so it does not process the same location more than once. For each current position, it looks at neighboring cells, and if a neighbor is inside the grid, not a wall, and not yet visited, it is added to the stack for later exploration. If the stack becomes empty without reaching the goal, the function returns false, meaning no path exists. We use a queue to perform a breadth-first search, starting by placing the initial position in the queue and recording that it has no parent. While the queue is not empty, we take the next position as the current one and check if it is the goal. If it is, we reconstruct the path by backtracking through the parent links from the goal to the start, then reverse the sequence to get the path in the correct order. If it is not the goal, we generate all neighboring positions, and for each valid and unvisited neighbor, we record the current position as its parent and add the neighbor to the queue. If we empty the queue without ever reaching the goal, we conclude that no path exists and return nothing. This script demonstrates how search algorithms can solve grid pathfinding problems. It represents a grid with open and blocked cells along with a defined start and goal position. The program first uses depth-first search to check whether any path exists from the start to the goal and reports the result. It then applies breadth-first search to compute one shortest path and prints that path as a sequence of grid coordinates. Together, these steps show how depth-first search answers the question of existence, while breadth-first search finds an actual shortest route. Communicating algorithm designs. Clear algorithm outlines. When explaining an algorithm, first give a simple, high-level story of what it does before mentioning technical details. Briefly state the overall task, then describe the main phases in plain language, such as exploring possible routes and choosing the best ones until you reach a destination. After this big picture is clear, break the process into stages like setting initial conditions, expanding the search, and stopping when the goal is found. This approach helps you understand the structure of the solution before worrying about syntax or optimizations. When outlining an algorithm, break it into clear phases that match natural subtasks. For example, in a product recommendation system, you might first gather user data, then compute similarity scores, rank products, and finally filter and present the top results. Describe each phase in terms of its inputs, how the data is transformed, and what outputs it produces, using simple language. This kind of step-by-step narrative makes it much easier to later translate the design into specific functions and logic without confusion. When explaining an algorithm, first walk your audience through the normal sequence of steps. Then cover special cases. For example, you might start with how tickets are received, categorized, prioritized, and assigned in a support system. After that basic flow is clear, you can describe exceptions such as missing information or unavailable agents. Make it clear where steps repeat, where the process branches, and where it ends so listeners understand how the system behaves in different situations. This structured approach builds a shared high-level understanding before anyone dives into technical details. Assumptions and invariants. When explaining an algorithm, it is important to clearly state its assumptions and invariants. Assumptions describe the conditions that must hold before and during execution, such as properties of the input or limits on resources. Invariants describe properties that stay true at key points, like after each loop iteration. For example, that part of a collection remains sorted, or a running total correctly reflects processed elements. Expressing these ideas in plain language helps clarify not only what the algorithm does, but also why it works under the given conditions. When explaining assumptions in algorithm design, connect them to real-world situations so their impact is clear. For example, a hospital's scheduling algorithm might assume valid patient IDs and non-overlapping time slots, which defines where it works and prevents use in systems that allow double bookings. In logistics, assuming stable travel times may be realistic for rail shipping, but not for ride-sharing in busy cities. By clearly stating such assumptions, you help others judge when the algorithm applies and make it easier to adapt when conditions change. Invariants are key properties that stay true throughout an algorithm and make its logic and correctness clear. For example, in a search algorithm, they can state which parts of the data have already been checked and which still may contain answers. And in financial risk aggregation, they ensure the risk estimate always reflects all portfolios processed so far. By showing how each step preserves these properties and combining them with the starting assumptions, you can explain why the algorithm works reliably and is appropriate for its task. This script illustrates a loop invariant using a running total over a list of integers. It assumes the list is non-empty and contains only integers. As the function moves through the list, it keeps a running total and counts how many items have been processed. After each step, it confirms that the running total matches the sum of the items seen so far, reinforcing the invariant. At the end, it returns and prints the total sum of the list, confirming that the process worked correctly under these assumptions. Complexity trade-off summary. When you present an algorithm, you should briefly explain how its running time and memory use grow as the input gets larger. This helps people understand not just how the algorithm works, but where it is practical to use. For instance, an approach that runs in linear time may be fine for a small business, but too slow for a global system. By contrasting a faster, more memory-hungry method with a slower, more space-efficient one, you help decision-makers weigh performance against resource limits. Overall, the goal is to describe complexity in terms of speed, scalability, and resource demands that matter in real-world systems. When comparing algorithms, it is important to judge their trade-offs in a context of how they will be used. For example, one route planning method might find the absolute shortest path but use more time and memory, which works well for overnight planning. Another might produce slightly longer routes but respond very quickly, which is better for real-time use on mobile devices. The key idea is that one option prioritizes optimal results with higher resource costs, while the other emphasizes speed and efficiency. Explaining these choices in terms of user experience and system limits makes the complexity trade-offs clear and meaningful. When discussing complexity trade-offs, focus on how an algorithm's performance changes with different usage patterns and future growth. An approach that works well today on a moderate dataset or for occasional analysis may fail if the data grows or the task must run continuously. It is important to point out when a simple, effective algorithm now may not scale as well as a more complex option that can handle larger demands. By connecting these trade-offs to both current needs and likely future changes, you help your audience choose an algorithmic design that will remain appropriate over time. In this lecture, you learn to decompose complex problems into subproblems that suggest suitable algorithmic techniques, select appropriate data structures and algorithmic paradigms for given Python problems, and communicate algorithm designs clearly using high-level descriptions and complexity analysis. Congratulations on completing this course.
Thank you for your attention. See you all in the next lecture.